Yesterday, I took a devastating loss to this problem right here. How devastating? Yeah. I have a test about this stuff on Monday, so I absolutely must stop this from ever possibly happening again. The only way to do that is to practice more of them. In this case, optimizations. These are really hard because they're basically related rates and systems of equations combined into one with a sprinkle of graph function shaped stuff. Let's begin. This is a sphere, constant radius r. This is the only thing you really need to know about it other than this cone inscribed within. Inscribed basically means that all of the corners of the cone are on the sphere, including the circular base, since you can think of that as like a bazillion corners. Now this cone is big, really big. In fact, let's just say it's as big as can possibly be given the constraints. How big is that? Well, we need some variables first. Right circular cones have a radius little r and height h. Orally, I'll denote the radius of the sphere as r and the radius of the cone as r, because my math teacher will shoot me if I mix up the two. And you'll arrive at a wrong answer, which also isn't great. Now this is a system of equations problem, so we must keep track of our damn variables. Alright, geometry time. Now drawing stuff in 3D is really hard, so we're just going to look at a cross section because their solids are revolution, so all the numbers are the same no matter how you slice them through the center. Let's sign off that center and slice the triangle in half so that we get two right triangles. These are easier to work with. This length is h, this one is r, and these lengths are from the center to the sphere, so they're r. We now have the volume formula for the cone, which is what we're trying to figure out ultimately, and now we're stuck because we have three variables and only one equation. V is who cares, we'll get there. But we do need more than just r and h. We can do this by calling r for help. Because it's a constant, it doesn't depend on anything, so putting it in our relations won't be an issue. Take this little length, which we'll call x, which is equal to the difference of h and r. Now this is a new variable, which means we'll need another relationship to solve for it, but it also creates this tiny little right triangle, which more than makes up for it. Calling the Pythagorean theorem gives us r in terms of x, and we have x in terms of h, and everything in terms of v, and boom. We done it. Now it's calculus time. Let's look at this completely random graph. You'll notice that the greatest point occurs when the line touching the graph is horizontal. This is because on the x-axis before the maximum it's increasing, so the slope is positive. Afterwards it goes back down, so the slope is negative. And in between these two states is where the slope of the tangent line is zero. Wait, go back a few seconds. These two states is where the slope of the tangent line is zero. Did you mean to say derivative there? Well, we have v directly in terms of x, so this holds true for that relationship as well. In other words, the maximum volume is when its derivative with respect to x is equal to 0. Equation, power rule, factor, zero product property. Make sure that your answer's in the domain. Now we've solved for x. We substitute, simplify, done.